So what we want to look at now is we want to look at when we're applying forces on our object, what can happen to our object. So if we put forces on our object, the first thing that can happen is we can pull or stretch our object. And when we do this, we put our object in tension. So whenever you're stretching or pulling the object, it's under tension. The other case we can look at is if we squash or squeeze our object. If we squash or squeeze, then we put our thing under compression. And so a simple example of looking at squash, tension, and compression is if you have a beam. If you have some beam and then you, let's say, apply some load here, some force load, you put an object on there, what would happen is the beam would, slightly bend. And so as your beam undergoes some type of deflection here, the top would be stretched, and then on the bottom up here, there's some compression. So the top gets stretched and the bottom gets squished together. And so when you apply some load to a beam, the beam undergoes tension and compression. So another case you can think about like this is if you had your beam, let's say you had some beam like this, and you have your support, and then you drop some load here, then what happens? Then the beam does, well, this is exaggerated and drawn poorly. The beam does something like this, and in this case now, the bottom is under tension, and the top is under compression. And so the idea is that whenever you start applying forces to things, you have tension you can have tension or compression, or sometimes both, in your system. Now, the interesting part is the bottoms and the tops do something, but there's a middle part in your system that actually doesn't change. Its location, the middle of your object, there are spots when you apply forces on things that don't undergo tension or compression. They stay neutral. So this dashed line I tried to draw in is called your neutral layer. And it's unaffected by the tensions and compressions. And of course, this neutral layer is what we take advantage of when we look at this shape. Because this neutral layer is used to take advantage of an I-beam. Because an I-beam, the top and bottom, these guys here, the top and the bottom, these guys here are the ones undergoing tension and compression. And these are undergoing the tension and compression in this middle. These are called the flanges. And the middle part, or the web, doesn't. The middle of the web is just the connecting piece, and it undergoes very little forces. It's just there to connect the top and the bottom that are undergoing all the tensions and compressions. And the reason that this becomes advantageous is the beam is missing this whole middle section. So the beam doesn't have to support any extra mass here. So you could imagine that this beam on the bottom here doesn't have to support all that extra weight. That extra mass and weight that would normally this bottom has to support, it doesn't have to support it, so therefore it can actually take an extra load because it doesn't have to support as much weight, self-weight. And so this is the idea. We can pull or stretch, which is tension, or we can squash, which is compression. Some part of the material, there's a part that is called the neutral layer that doesn't get squashed or stretched, and we take advantage of that concept when we have something like an I-beam. Now, another part of tension and compression is that certain materials do better under one or the other. And an example of something that does better under compression than tension is stone blocks. And so what happens is stones, not that they do better, but they can take a much larger compressive force than they can a tension force. And so we take advantage of these compression forces on stones initially a long time ago because we built something called, what I have drawn poorly here. We have done this, actually let me correct my arch as best I can, but we built these things called arches. And arches take advantage of the fact that all the blocks are constantly undergoing compressions. And the compression actually pushes and squashes the blocks together, holding them in place and keeping them tight. And because the stone has a much higher compression strength, it actually can take, on top of the compression holding it together, when you, let's say, use this, you can actually use arches to support loads over the arch because as you add weight to the arch distributes the compression evenly through the stones, and the stones can withstand it because they have a high compression strength. Now, this of course is why for a long time, like you look at ancient civilizations, like the ancient Greeks or whatever, they used to use lots of pillars to support roofs on, let's say, temples or whatever. And then you'll notice that at some point, once we introduced the arch replaced all those needs for pillars because you could get away without needing all those pillars because the arch could support a much larger load. And then you actually look and see arches are very sturdy and stable. They even still have some, the Romans used arches extensively. You can see it like in all their aqueducts and things like that, and some of those things are still standing today. Now another thing to think about is if you take an arch and you rotate it through 360 degrees, you get a dome. And why are domes so useful? Because domes enable us to put roofing over a large area without having to introduce a support column or beam. And these, of course, become useful like in stadiums because when you want to watch two teams play against each other, you wouldn't want to have to be like having columns in the way that people have to like run around in the middle of the game. So domes are very useful because the dome takes advantage of the arch shape, which enables them to cover that large area without needing support columns. And so this is just another, domes and arches are examples of the idea of tensions and compressions where stones can take a much larger compression, and so they took advantage of that and built this shape. Because of the compressive nature, you can add that extra load or the fact that the arch will support itself rather easily because of that compressive nature. The blocks actually lock themselves together and they hold themselves in place because they undergo compression instead of tension. They don't pull apart, they get forced together and they get locked in place.